Hi everyone and welcome to this new video. In this video I want to do a deep dive over how pointers work in the C programming language. Therefore you can expect in this video that we will talk about memory, about what is memory, how it is structured, and a lot of stuff with respect to how we can work with memory from a C program. Then we can see how pointers work in the C programming language, because of course pointers are linked to memory. And finally, we will talk briefly on why C is not a memory safe language. I hope the video is interesting and you get something out of it. If you do, subscribe to the channel, share this video and this channel with like-minded people to help me grow. Thank you and enjoy the video. So let's start our discussion by talking about memory. Because to properly understand pointers in C, it is fundamental to understand the basics of memory. After all, pointers are a way to interact with memory, to read and write memory. So basically, we need to understand the following question. First of all, what is memory? Second, how is memory structured? And third, what's the difference between a value and an address? So here we will go point by point to understand this fundamental concept, and once we have discovered, we can actually see some C code and some pointers in the C language. So what is memory? Now you can think of memory as a place in your computer where you can store bytes. That is, memory is made up of slots, and in each slot you can write an arbitrary byte. Now what is a byte? A byte is just a sequence of 8 bits. And this means that with 8 bits we can represent 256 values from 0 to 255. So here you can see the mapping between the sequence of bits and the decimal number. We can also write it in hexadecimal, it does not really matter. Basically, the idea is that with 8 bits we get from 0 to 255, that's a single byte. So basically, a memory is a container of bytes. And this can be called in different ways. You can call it a sequence of cells, a sequence of slots, a sequence of locations. Basically, the intuition I want you to know at this point is that with memory, you have a bunch of these slots, a bunch of these places where you can write bytes, and each one of those is 1 byte. So 1 byte, 1 byte, 1 byte. And if you zoom into that single byte here, you get 8 different bits. So you get 8 0 and 1s. So basically, that's the first image I want you to imagine, just a sequence of slots. Now, how is memory structured? Now, what's the cool thing about memory? The cool thing about memory is that we can specify where we want to store our values. That is, values in memory, they don't just exist in random positions of the memory. They exist in specific positions of the memory. I can have a specific byte as the first cell, then another byte in the 250 cell, and so on and so forth. Imagine the following table. We have addresses on the left and values on the right. And each value belongs to a specific address. So this is the slot I was talking about. Each slot has a specific address, and in each slot we can write a single byte, which is made up of 8 bits. And here, of course, we can keep going because we have no limits whatsoever in terms of the amount of memory. Now, of course, when we work with physical memory, at some point, this has to stop because we cannot invent infinite hardware. We are still limited, sadly, from the finiteness of our world. But basically, the idea is that you can imagine this process keep going forever. So as you can see, in every row of the table, in every row of memory, we have two kinds of information. We have the information regarding the address, which represents the specific location in memory that we are working with, that we are referencing. And then we have the value, which represent the content in that specific region of memory. So memory is just a very big table of bytes where each byte has its own address. So basically that's the main intuition I want you to have at this point. Memory is just a bunch of bytes, each byte has an address. Now, when you deal with addresses, you often see values like the following, like this one, consider this one. 0x7ff8 2e11160. Now, why do we use hexadecimal notation when describing memory addresses? And why don't we simply use decimal notation? I mean, consider the simple example that I showed before. Here we just use decimal notation because after all, we just want an increasing integer, like 0, 1, 2, 3, 4, 5, 6. So why specifically are we so obsessed with hexadecimal? Well, of course, there are a bunch of reasons that make hexadecimal a really good notation. First of all, remember that we can write it in hexadecimal, we can write it in decimal. It does not really change the underlying number we are talking about. What changes is just the representation. So for example, this value, which is written in hex, refers to this number when we write it in decimal. So the number is the same, the notation is different. Now, why do we prefer hexadecimal notation when working with memory? Well, basically the idea is that the size of memory in modern computer is quite big, and hexadecimal allows us to describe big number with fewer digits, because each digit in hexadecimal can represent 16 values, 16 from 0 to f, because we have from 0 to 9, so that's 10, and then we have from A, B, C, D, E, and F. That's like what? That's 6. So 1, 2, 3, 4, 5, 6. That's 6. And that's in total 16. So first reason is that hexadecimal allows us to capture bigger numbers with fewer digits. But that's not really the killer reason. That's not really the main reason. The main reason is that hexadecimal notation allows us to quickly understand how memory addresses are aligned with respect to a certain number of bits. And basically the idea is that 16 is a multiple of 2, so by seeing in practice the hexadecimal number, the hexadecimal notation, we can understand if they are aligned with respect to a byte, with respect to 2 bytes, with respect to a given amount of bits. Because basically, I mean, if we want to go from this address to the bits that make up this address, what we can do is, it's like we start from this. Now we can remove the 0x with just a simple notation to describe that we are dealing with hexadecimal notation. Then we can take every couple of digits, and basically the idea is that every couple of digits represents a single byte. So this 7f is a single byte, this ff is a single byte. If we want to understand the binary of each of those bytes, essentially the binary notation, we can just split them up in sequences of 4. So here we have 4 bytes to represent 7, here we have 4 bytes to represent f. Now in this case, f is just literally 1, 1, 1, 1, all 4 ones. While 7, what is 7? Well, 7 is 6, so in that case we will be 0, 1, 1, 1, because we have 4, 2, and 1, so we have 7. So we have 7 and we have 1, and basically if we look at the first one, we can quickly go from hexadecimal to binary very, very fast. And we can do it with every digit whatsoever. So basically, the takeaway here is that since hexadecimal is a multiple of base 2, because hexadecimal is base 16, and 16 is 2 times 8, we can quickly go from hexadecimal notation to binary notation and vice versa. So it is extremely useful to see how memory is aligned and to do a bunch of operations just on the hexadecimal bytes. So this is why we use this notation. The point here to understand is that there's nothing magical about hexadecimal. It's just a notation that is useful to use. You can also consider the decimal notation as well, because at the end of the day, addresses are just numbers. This thing is just a number, identifying a specific location in memory. And we have first location, second location, third location, fourth location, and so on and so forth. Okay, so now the image we should have is that memory is a table made up of addresses and of values. So basically that's what I want you to know at this point. Now I'm gonna make a disclaimer, and I'm actually gonna say that the stuff is actually way more complex than this. Memory in reality is not just a big table in the way that it is implemented by the operating system. So let's read through this disclaimer. While the idea of imagining memory as a big table of bytes is a good first intuition for understanding pointers in C, the way memory is actually implemented in modern operating system is way more complex and requires more concept to be completely understood. Now, this video is not about how memory works in an operating system. It is about how pointers work in the C programming language. Now, the C programming language has an abstract view over memory. Why? Because there's this concept called virtual memory. Now, when a C program interacts with memory addresses, it does not actually see the physical addresses that are being used by the CPU to access the RAM hardware component. What the C program sees actually are the virtual addresses. Now, using virtual addresses allow different programs to share the same address values, even though in the underlying physical memory, they actually use different addresses. This thing is a very good abstraction offered by the hardware architecture and also supported by the operating system. Basically, the idea is that you have to imagine for every process that you run, you have a table similar to this. You have this table for process 1, you have this table for process 2, you have this table for process 3. Now, of course, different processes will have different values in memory. The question is, what values will they have in the address sections? Because when they actually execute in the RAM component, they will take up a different section of the RAM. For example, P1 can go here, P2 can go there, and P3 can go in another place, and so on and so forth. But basically, the idea is that by using virtual memory, every process sees the same address values. The address values are the same. For example, P1 can use 1 for a certain reason, P2 can use the same address value, but for a different value. So we can have the same addresses with different values, because each process has its own memory. It is an abstraction over real physical memory, which is why it's called virtual memory. But still, the basic idea is that with this, with virtual memory, it allows the C program to just see a flat list of memory. This is why we can imagine memory like this. In reality, it is not really like this, but thanks to virtual memory is the abstraction that makes this concept actually work out. Because when you're programming in C, essentially this is what the C program sees. This is what it sees, because there's virtual memory underneath. Now, to support the concept of virtual memory, you have a bunch of different components, such as page tables, which are used when translating a virtual address into a physical address. So they are very key data structure used by the kernel of the operating system, for example, by the Linux kernel. And this is implemented in the operating system. So this is supported by the OS. But there's also hardware support. For example, there's a specific component in the CPU called the TLB, which stands for Translation Look-Aside Buffer, and this is used to speed up the translation process. It is a cache that is used to store recent address translations, so that instead of all the time fetching the page table, you can quickly translate through the TLB. Now, this is all to say that thinking of memory as a big table made up of addresses and value is an abstraction. It is implemented by the operating system and supported by the hardware architecture. Now, for the C program, memory is a big table, which means that to actually understand pointers in C, you can just use the big table idea. However, as you dig deeper into system, of course, you will need to understand other concepts as well. As I said, it's not this simple, but this is a good introduction to understand how pointers work in the C programming language. You can just consider memory as this kind of image, addresses and values. But in reality, things are not this simple, to keep in mind for the future. So let's talk about, okay, we said that memory allows us to store single bytes of information. However, sometimes it takes more than 1 byte. So most of the data types are actually bigger than 1 byte. If you have a car, a character type, Now this is typically 1 byte in most of the architecture, right? So a car means that a car can simply go into a single slot in memory, and that's it for the car. However, let's say that we have an integer, an int. In this case, typically integer, like a signed integer, require 4 bytes of memory. So what's the catch here? What can we do if we want to store something that is bigger than 1 byte? Now, when we have a data type that is longer than 1 byte, we can still store its value. We just have to be careful in the way that we use the cells of the memory, in the way that we use the memory addresses. For example, consider that we want to store the famous integer dead beef. This is like a funny joke because in hexadecimal this actually represents a word, dead beef, but this is also a number because it just uses letters from from A to F. Now with this integer, we can store it as follows. So we can store it into different cells. So like 1, 2, 3, and 4. We can store it the DE, then the AD, then the BE, and then the EF. So basically what I want to say at this point is that it does not matter how big data is. We can still split it up into atom of 1 byte each. Now, there is a distinction to make here between different hardware architecture, whether they are little endian or big endian. So there's little and big endianness. And these essentially have to do with respect to the order in which these bytes are stored. Now, I always forget about the specific association, but basically the idea is that when you see the big number, like written like this, you have the most significant byte on the right, the most significant bits on the right, and the least significant bits on the left, right? You're gonna have something like this on the left, and you're gonna have something, something like that on the right. Now, if you are one way or another, essentially what matters is how this sequence is split up. So I just did a quick check on Wikipedia and it said a big endian system stores the most significant byte of a word at the smallest memory address and the least significant byte at the largest memory address. So basically it's what I've written here. We have address 1, 2, 3, and 4. We have the most significant byte at the smallest memory because the E, the one on the left, is the most significant byte and we store it at the smallest. And EF is stored at the largest memory address. A little endian is the opposite. It means that we would first find EF, then BE, then AD, and finally DE. Why do we have to make this choice? Because, as we said, memory works with atom of 1 byte. So we can store any value we want. We just have to decide how do we split it up. And here, by the way, a word is just a sequence of bytes. It can be 4 bytes, it can be 8 bytes. Typically with a word, we refer to 4 bytes specifically, but it can be also longer. So basically, the idea at this point is that it does not matter how big are the data types. We can store any data type of arbitrary length by just using adjacent sequence of single byte cells. And then, depending if you are storing a little endian or a big endian system, we might have different orders. But that does not really matter. It's just like a specific thing on architecture. Finally, I want to talk about the differences between values and addresses. And this is one of the most key ideas to understand pointers properly. Now, at this point, you might think that values and addresses are two completely different things, because the way I introduce them is like, okay, how is memory structured? We have addresses that represents the specific area in the memory, and the values that are the actual value that we store in that specific region of the memory. So addresses are like index for regions, right? Like first region, second region, third region. So in part, it is true that they mean different things. When we talk about a value, that is not an address. An address has a specific meaning. A value, it can be anything. However, the cool thing about computer science is that underneath it all, we just have sequences of bits. We mostly deal with raw information. And this is really what gives computer science its amazing expressive power. It does not matter what we are dealing with, we are just dealing with bits underneath it all. That is, both values and addresses can be represented using the same methods. We have a bunch of bits, so we can use them binary notation, we can use decimal notation, we can use hexadecimal notation. I mean, to be honest, at the end, underneath it all, we just have physical phenomena like transistors getting on and off. So basically, we can represent these things with typical notation. This means that an address is just a sequence of bits. A sequence of bits is just a number. This means that an address can be stored as a normal value in memory, because the memory just contains bits and the address can be itself represented as bits, which means that those bits can also refer to other addresses in the same memory. So this is the most critical point to understand. Memory is made up of cells. So that's the image that we have. Memory is made up of cells. Each cell has an address and a value. So this is the address and this is the value. This is the address and this is the value. This is the address and this is the value. The address is a number, while the value is just a sequence of bits. Like here, 42 is just a sequence of bits, 53 is just a sequence of bits. Numbers can be represented using sequences of bits. Addresses too can be sequences of bits. It's like an address is a number, but a number is just a sequence of bits. This can be confusing, but the basic idea is that from this, we just get, 00001, whatever. This means that memory addresses can be values stored in memory. This means here that I can have, for example, let's say I have the fifth address in memory that stores 1, and 1 is the address of the first cell in memory. And this is the basic idea of pointer. This is exactly what a pointer is. A pointer is a place in memory, a so-called variable, a place in memory. It can be on the local memory, it can be a global variable, it can be whatever. It's just a place in memory, it's just a slot or a sequence of slots, right? That stores a memory address. So it's just a cell or a sequence of cells that store a memory address. Because of course, in this case, I just put 1 in a single cell. But as we said, typically, pointers are longer than 1 byte. So we might need more cells to store a pointer, right? But basically the idea is that the pointer, taken as a single value, can point to a different portion of the memory. And with this, we cover the fundamental ideas on memory. At this point, we can actually see some C code. Let's consider this extremely simple example. Here we have a simple program that prints an integer. This integer is defined in the local function of main. And here we include the stdio to just printf, to just do a printf. We can compile this code with GCC and we can add the debug information so that we can debug it with GDB. Now to understand, to get familiar with pointers, let's get familiar with memory in a C program. So we can start to ask the following questions, for example. Where is the variable a stored? How big is the variable a? Let's analyze it with GDB. Let's analyze everything with GDB. So if we just compile and execute this code, so here I have the code on the left, the compilation buffer up, and the shell on the bottom here. I have compiled the code, I can just execute it, right? To actually check the size of the memory of this int, I can use this thing of C, size of A. Essentially, it's gonna give me another integer. I'm gonna print it. It says 4. Because an integer has a size 4 bytes in this specific architecture, which is an Intel x86-64, so a typical 64-bit architecture. Now, let's debug it with GDB. So, I've made a video on how to use GDB, so here I'm gonna go a bit faster. So, just gonna start it without any sort of prompt. As you can see, this is a minimal program. We just have the main function defined in our file. So let's disassemble it. Let's do a disas main. And here we get the disassemble code of the main function. Now I've made other videos describing the function prolog, calling convention and things of the sort. Now basically what we are interested in at this point is the fact that when the program does this sub rsp 0x10, it's gonna take up a place in the stack of the program, and the stack of the program is used to hold all the local variables. So all the local variables are going to go into this stack frame for the main function, and basically this just creates that exact space. Then, as you can see here, we do a move, so we take this static value, this 0x539, and we put it into the memory region that is addressed by this value, by the value of the register RBP, when we do minus 0x4. So this syntax in the Intel syntax essentially means you take this value and you write it into this memory address. So you take this value, you compute this value, which is just a number, and you write into the memory at that address, at that index, this particular value. Now, what is this value? What is 539? Of course, it's 1337. How do we know for certain? We can just print it into decimal format, 0x539, and look at this, we get 1337, of course. We get the lit. Now, let's, to actually understand this, let's just put a breakpoint where, let's just put a breakpoint at main plus 8. So do main star b main plus 8. So with this syntax, we put a breakpoint at that thing. Now we can run our program. It's gonna break, of course, at that level. So we can do this as main again. Now we are on this layer. So we still have to write that particular value into memory. Now, what is the value of RBP? To check the value of RBP, we can do echo RBP like this. Actually, not like this. I think it's print RBP. So print RBP, and we get essentially this value. So this is the, we can also do, I think, info, register, and then RBP, maybe. Yes. So as you can see, this is the value of RBP. It's hexadecimal, it can be confusing and scary, but at the end of the day, this is just a big number, an extremely big number. But the actual region in which we write our value is not RBP, it's RBP minus 0x4. So we actually want this, so we want to do print RBP minus 0x4. So this is the actual cell in the memory where we're gonna write our value. And we can also like just print it in decimal to remember that everything that we have in hexadecimal ultimately is just a big number. We can also write it in decimal. Now, let's check what is contained in that region of memory at this moment in time. So at this point before actually writing the value. And how do we do that? Well, we can use the X command in GDB. Specifically, I want to check byte by byte the memory area. So I want to say, okay, look, I want 4 bytes. So here I'm going to say 4B, and I'm going to want to print them in hexadecimal, starting from RBP minus 0x4. So that's the basic idea. And look what we have here at this point. We have these 4 bytes. We have FF, 7F, 0000. So what's going on here? Well, basically the idea is that this value was used to access the memory, and you can see here on the left. Now, this cell 0xFF is actually the byte that is written exactly in this cell of memory. The next byte 0x7F is written in the next memory area. So like not in this address specifically, but in the next one. Now, what is the next one? Well, consider the end of this address. We have 4, 6, C. The next one is going to be 4, 6, and what's after C? Well, we have C, D. So we have D. It's going to be 4, 6, D. The next is going to be on 3, like it's going to do plus 2 starting from this one. So it's not going to be D, it's going to be E, 4, 6, E. And the next is going to be 4, 6, F. So basically in this GDB compresses this view, it does not give us like literally for every byte the address, because otherwise we would go crazy. But for example, let's say that we get, I don't know, 8 bytes. Notice that we still get in the same line. Now, if we had to ask 16 bytes, notice that we will get 2 different lines. Now, this is just a it's sort of like a formatting method used by GDB. At the end of the day, you can take this view, which is more condensed, more compressed, and obtain the more explicit address value view, essentially. And this is a good skill to learn when you are debugging in GDB, to just do it on your head. So basically that's the idea. Now at this point though, we still have to write the value itself, right? So let's go ahead with this write and let's see what happens afterwards. So I'm gonna do next I, so next instruction, and I. At this point, I did write the value. This instruction is executed. So let's see the memory. And look at this. Now it changed. It changed. These 4 bytes now have changed, because now, of course, the last 2 here, they're still 0. But this first, now they are 39005. And actually, remember this, it was 539. Why? Because this is a little endian architecture. So the thing that we're going to write first is not the most significant, but it is the least significant. So we write them in the reverse order. So if we have a bunch of bytes here, we're gonna write them in reverse order. When we read the entire value together, we're just gonna read the bytes, flip them, and that's our actually numeric value. So at this point, we have written in memory this value. And what does it mean, essentially? It means that in our memory view, at this point, what we have? We have that at this specific address, so if you just want 1 byte in hexadecimal at this specific address, we're gonna get 39. And at the next, we're gonna get 05. So this is what we have at this point. Now we can talk about pointers actually, right? Because this is a simple example. This is just to showcase that memory at the end reduces to a big table of addresses in blue and values in white here. That's basically the idea. And when we say that an int is 4 bytes, it means that memory-wise, we can write with an int only these 4 different values. We can write all these values, but we cannot write, for example, the next byte, because we just have 4 bytes of space. Now, at this point, we can actually see some pointer-related syntax. Now, when we define a pointer type, we do a variable, a typical data type, followed by this asterisk. And then we have the typical name. So let's do this. So let's do this thing, and then we do this operand. So we have essentially this thing. And then here I want to just print this PA itself. So I just want to do print, and I'm gonna print in this particular syntax. So let's close this. Yes. Let's recompile everything and let's execute the program. So look at what we got. We just got this hexadecimal value, which is an address in memory. Now, why did we get an address in memory? Well, because the basic idea of pointers is that they are variables like any other variable. However, their value is not the value of this A, which is 1337, but it is the address of this other variable. And when we do this operand, this e-commerce, like this commercial end, basically, we are extracting the address from the variable. What does it mean to extract the address? Well, let's debug this new program, but basically it means that this variable had this address. So now we're gonna get this thing and we're gonna put it into memory as value. So basically that's the idea, but let's see it in practice. So let's do once again simple. Let's discuss the main. Now, when we look at this assembly code, what do we see? We see the same static 0x539, which is going to be the hard-coded 1337 in our code. Now remember, however, that we're also referencing the address of this other variable. And this other thing actually happens to be this RBP minus 0x10. So what is going on here? Look at these instructions. Just look at these 3 instructions. First things first, we put the 1337 into this particular region of memory. Then we do a load effective address. We are loading the address, so we are not referencing the memory. We are just writing the address into racks. And then we are writing racks into the memory. So we just wrote into the memory the value of this computation, RBP minus 0x14. This is the address of the variable in which we wrote 1337. So let's put a breakpoint to understand it further. So we do break main plus 23. So we do okay, we do a run. At this point, we have the this kind of thing, right? Int a equal 1337, and we know that this variable is going to be located at this memory address 10x, so like RBP minus 0x14. So let's print 4 bytes in hexadecimal starting from RBP minus 0x14. So this is before writing the value. We do next instruction, and look at this, it changed like before. So this is what we had even before, nothing new here. We have the value written as these 4 bytes, in which the last 2 is going to be 00, and the first 2 is going to be 3905. When this is assembled and read as a little endian integer, this is going to be 0x0539. I mean, technically this would be 0x 00 because it's this one, 00 is this one, 05 is this one, and then 39, which is the first one, which becomes the last one. But of course, all these zeros have no sense mathematically. They just are 0, so we don't need to write them. So this is 0x539. Perfect. This is exactly what we had before. But now things change because we have introduced the concept of a pointer. So when we write this kind of thing, what is going on underneath our program? What is going on in the process? Well, so what's going to happen now? Now we're going to execute this load effective address. So we're going to load into racks this particular expression. Now, if we compute this expression, if we just print out this expression, RBP minus 0x14, notice that we get here this value, and this value was the address of this integer, right? It is 7 all f's E45C. It is the same thing. When we do the load effective address, so let's print now the value of the register racks. Now it's 0, 0. We have nothing in racks. After we execute this thing, we're gonna have the address of that variable in racks. We do next instruction. We print once again the value of racks. And now look, the value of racks contains that particular address. So now the address is in the racks register. The next thing, the last instruction is this one, is this plus 34. And we're gonna take the value of racks and we're gonna write it into memory at this particular area, RBP minus 0x10. So let's do this. Next instruction. At this point, if we check the memory at the, let's do 8 bytes in hexadecimal of RBP minus 0x10. So look at what we have here. So first of all, why did I say 8 bytes and not 4 bytes? Because we know that an integer has 4 bytes of memory. Now the question is, okay, but how big is a pointer to an integer? So let's try to answer this question. Okay, a pointer to an integer has to contain the address of the integer. Okay, so basically that's the idea. Now, in our system, we have 64 bits of memory. It means that the address can be any of the 64 bits combination. I mean, in practice, this is not really true, but let's assume that it is. How many bytes does it take to represent 64 bits? Well, each byte is 8 bits, and I do 8 times 8, and I get 64. So I need 8 bytes to represent 64 bits, which means that to store a pointer for a 64-bit system, I need 8 bytes. With this reasoning, I can assume that the space here required is 8 bytes. So an int star is gonna take up in memory 8 bytes of space. Now look at what we have here. We have exactly 8 bytes. They are of course divided, and if you analyze them, look at this. We have 0f, 7f, which is this 7f. Then we have ff, which is this ff. We have another ff, and then at the end we have 5c, and then we have e4. Essentially what we did is that now we have written the address of a variable. So remember that this is the address of the variable. We have written it into memory as another value. And of course, we can view it as broken like that, or we can view it in a more compact syntax by saying I want only one item, but I want this to be a giant, which means a block of 8 bytes together over the same starting point. And look at what we have here. Essentially, we have exactly this address. It's just that in this syntax, we also put the initial zeros, which mathematically, they do not matter, they are the same value. So, what's the difference between a value and a pointer? Well, if we check, so if we do this, essentially, RBP minus 0x14, here we have all the stuff that matters. So actually, let's print it into decimal. So let's print it into decimal and let's print the address of that variable. So just focus on the last two. Just focus on these two. The first line represents a direct variable. So in the direct variable, we have a pointer that holds a specific value. The second line represents a pointer. What is a pointer? Is a variable whose content is the address of another variable. So this is why pointers can be confusing, because they add a level of redirection. When you have simple values, you just have the address and you have the value. And you don't really care about the address, you just want the value. And the address is just a means to store the value so that you can retrieve it without losing it. When you're talking about a pointer instead, things become more confusing because you have a level of redirection. You are not referencing the value itself directly, you are referencing the place where the value lives in memory. This place is itself a value. So this is the redirection that happens. When you read a pointer, you are going through a specific memory address. This is the memory address where the pointer is stored. Because of course the pointer, after all, is just another variable, which means that it requires another address to be stored. The value of the pointer is the address of the variable you're pointing to, of the value you're pointing to. So this one has this little redirection, and finally you get your value. So basically that's the idea. The syntax, so let's compare the C syntax and the what's going on in memory. Here we are defining 1337, and this is what happens underneath. We have an address with a specific value. Here we are defining a pointer to that particular variable, right? Because we are saying take the address of this variable. And what's going on in memory? We take a different cell, a different region. We don't care about this address. This could be any address whatsoever. What we are interested in is the value itself of this address, because this value is the address of the variable. It is the address of the A variable in this case. So basically that's the idea. Now, when we work with pointers, we have different operations that we can do with the pointer. And for example, this thing, this operand, is used to take the address out of a variable. But we have different operations as well. Basically, we have these following three main operations. First, we define the pointer type. And by the pointer type, we just mean a pointer of different types. We have a pointer to integer, we have a pointer to float, we have a pointer to character. So this is how we do it. We just take the base data type and we add an asterisk. And with this, we define a variable whose value is going to be the address of another variable. In the case of a pointer to integer, it's going to be the address of an int variable. In the case of a pointer to float, it's going to be the address of a float variable. In the case of a pointer to char, it's going to be the address of a char variable. The second thing we can do is we can extract the address of a variable and we can assign it to the pointer with this syntax, the one that I already showed. Finally, to access the value pointed by a pointer, we can perform the difference operation. When we deference our pointer, we access to the underlying value. And how do we do this operation? We take our pointer type and we put an asterisk to the left. This is called dereferencing. So this is the dereference. Now, how does the reference work? Basically, the program is going to do this. You're going to say, okay, I start with PA. Now, PA is a pointer. The address of the value of PA is this thing, and the address of PA is this other thing. To dereference, when I do this scanning with the asterisk, the idea is that I go to the value, I resolve this address, and I go to the value pointed by that address. So in this case, it would be 1337. So by dereferencing this, I get 1337 back. I get the value pointed by the variable I'm pointing to. So at the start, this can be a bit confusing, but basically, this is the idea with pointers. Now, we can talk about pointer arithmetic. What's the basic idea? Let's assume that we have an array. So let's do that. A now is an array of integers. Let's say we have 0, 1, 2, 3, 4, and 5. We have a bunch of integers, right? And then we can define a pointer A like this. Now, when we talk about arrays, we can just use this kind of syntax, and PA is going to point to the first element of the array. Now, let's say that we print, so we can print now the value of the pointer, like this. We can print the value pointed by the pointer, so we can actually do this kind of syntax. So with this printf, we print the pointer and the value. So let's just do simple like this. So look at that, we have the address of the first member of this array with its value. Now, what pointer arithmetic allows us to perform is a way to go to the next value. So what's the idea? Let's say that I do PA equal PA plus 1. So I've added 1, but to a pointer type. Now this has special meaning. Why? Because the compiler knows that we are not dealing with a normal value. We are not dealing with a normal data type. We are dealing with a pointer to a data type. We are dealing with a pointer to integer. How is this actually interpreted by the compiler? How does it work in practice? What's the final program gonna do? Well, let's print it out. Let's just print it out to see how it changes. I do simple. Notice what happens. the value of the pointer was not incremented by 1. It was incremented by 4 bytes. It was added 4. We go from CC0 to CC4. And the value now pointed is 1. It is the second element of the array. If we keep going, what do you think we're gonna get? Well, at this point, you can probably try to guess. Look at this, we have 0, we do plus 4, and then we do another plus 4. So we go 0, 4, 8, and we get 0, 1, 2. So what's the idea here? Well, the idea is that when we increment by 1 the pointer, the underlying pointer is actually going to be incremented by a value that depends on the size of the pointed variable, of the pointed type. What does it mean? It means that this is a pointer to an integer. Integer has 4 bytes. When we do plus 1, we're actually increasing of 4 the pointer value. Why we're doing this? Because as we said, memory works in multiples of 1 bytes. So we just have 1 bytes. Since this points to an integer, the compiler is gonna say, okay, you do plus 1, you want to point to the next integer in memory. So the next integer in memory is not the one 1 byte after the initial pointer, is the one 4 bytes after the initial pointer, because each integer is 4 bytes. For example, what would happen here if I have an array of character? So look at this character. So here I have A, B, C, D, something like this. So here I have an array of characters like this, and here I do char like this, and here I do char like this, like this, like this, like this. So what happens at this point? Well, now if I compile it, look at what happens. Well, I still get the first, second, and third element of the array, but now the address was incremented by 1, not by 4 anymore. So you gotta be careful when you do pointer arithmetic, because here you're doing a plus 1, but this plus 1, semantically, it depends on the type of the pointer. What kind of data type you are pointing to. If it's a char that is a size 1, we're gonna increment 1 the pointer 2. But if it's an integer, which is size 4, we're gonna increment 4 the pointer. What instead if I had an array of long? So let's do long. So let's do long like before. 1, 0, 1, 2, 3. It doesn't even matter how big they are. Let's just do long like this. And here I'm going to say L. And notice now, I go from 0 to 8 to 0 again. Because at this point, the jump plus 1 is actually of plus 8 in terms of the memory address. This is because a long is 1, 2, 3, 4, 5, 6, 7, and 8. It's just this big chunk. You go to the next long, you're going to increase by 8 the pointer to go to the next 8, to the next sequence of 8 bytes, which is another long. Basically, the idea is, in memory, we just have sequences of bytes. But then, depending on how you want to work with those sequences, you can use pointers to consider this memory and to cast it to different sizes. For example, you can say, I want to work with a long, and so you're going to get 8 sequence, like 8 adjacent bytes, and you're going to work with them. And then you can say, okay, but now I want to consider the single bytes of this sequence. So I'm going to have a pointer to a char, and I'm going to point one after the other. I'm going to work one after the other. Basically, the idea is that the single sequences of bytes, the single bytes of memory, can be grouped in different ways. And when we do a plus 1 or a plus 2 or a plus 3 or a minus 1 or a minus 2, the way we're actually modifying the address depends on the type of data that we are pointing to. Now, to finish off the video, I want to briefly mention why C is not a memory-safe language. Now, by using the pointer syntax, C allows you to access in read and write mode every portion of the program's memory. Because as we said, program's memory is just a bunch of bytes. If here I look, for example, at 100 bytes starting from the stack, from the RSP, and I want them in hexadecimal, look, here I get 100 bytes of memory, but I can even get 1,000 bytes of memory. I can even get the entire memory like this, right? The entire memory of the program. This is just the memory of the program. And with C, I can change each one of those bytes if I want. I just gotta get the address, which I can guess or do randomly, and I can just change all these things. It is extremely powerful. So this is an extremely powerful ability. However, of course, with power also comes dangerous effects. Now, specifically in the context of C, we're talking about memory corruption vulnerabilities. which happens because a C program does not properly handle the management of memory, and this will end up corrupting internal states and causing security issues. Now, I've actually talked about this in the video on my Linux privilege escalation series when I talk about Linux binary exploitation. This is because these types of attacks, binary exploitation attacks, are used to do privilege escalation, are used to cross security boundaries, to gain more privileges and to own a system. So what's wrong with this program? Well, this is a very simple vulnerable program that we can take and we can compile. So let's create vuln.c. Gonna take this and then we're gonna compile with all these flags which just disable security mechanism. This is just for teaching purposes. So I'm gonna compile like this. Actually it says, no, it's not vulnerable, but it is vuln. It is vuln. And it is vuln like this. Perfect. At this point I can execute this vulnerable program. Now if I just execute it normally, nothing happens. So why is this vulnerable? Well, because if I give it a long enough input like this one, if I give it a long enough input like this one, look at what's gonna happen. So, let's look at what's gonna happen. It's gonna say segmentation fault. So the program had its internal state corrupted and this caused a crash of the program. Now, by being smart enough, you can use this kind of behavior to obtain a shell, to execute arbitrary commands in your system, and this opens up the way for a privilege escalation. And with respect to why this program is vulnerable, it is because it copies the user input buffer into a local buffer, but there is no check to make sure that the user input buffer is less than or equal to the destination buffer. Specifically, in this vulnerable function, I define a buffer of 512 bytes. I copy the entire user input, which I get from the command line. However, there is no check, there is no logic that validates the data, the length of this user input to make sure it is less than or equal to 512. It means that the user can write an arbitrary large amount of data. I'm gonna copy it into this buffer. At some point, the single bytes are gonna be over, but I'm gonna keep copying. And by keep copying, I'm gonna overwrite sensitive data structures, and this will crash the program. And this is because in C, at the end of the day, you just have a linear array of addresses and values. That is how pointers work. That is why C is such a powerful language, but that is also why C is such a dangerous language if you are not used to deal with memory management. And if you're interested in how to exploit that, you can check out the video on the Linux binary exploitation. And so this is it for this video. In this video, we discuss about memory and about pointers, and I hope that I provided some intuition with respect to what is exactly a pointer and to what is memory and to how you can explore memory with a tool such as GDB. This can be extremely helpful to build intuition over these complex topics. If you liked the video, subscribe to the channel and to the next video.